Energy. It powers your lights, your phone, and your car. Mountains of weather, engines, and living cells all run on different forms of energy. Thermodynamics is the science that describes how energy moves, changes form, and limits what's possible. Today, we'll learn the language of energy, systems and surroundings, heat and work, and two fundamental laws that rule all energy transformations. We'll use simple drawings, everyday examples, and a couple of thought experiments to make these ideas stick. No equations you can't handle, just clear intuition and a few neat visuals. Ready? Let's dive into the science of energy. In thermodynamics, we always pick something to study. That something is called the system. Everything outside is the surroundings. The boundary between them can be a real wall, like a pot, or an imaginary line, like the air in a room. Consider a cup of hot coffee. If the coffee and cup are the system, the table and the room are surroundings. Energy crosses the boundary. The coffee loses heat to the cooler room, and the cup may do work if it expands or if you stir it. Choosing your system carefully makes questions easier. Are you studying a battery cell? Pick the battery. An engine? Pick the engine and its gas. The rest becomes the surroundings. Energy is the broad idea, the capacity to do something. But in thermodynamics, we care about how energy travels. Two main ways: heat and work. Heat is energy that flows because of a temperature difference. If your coffee is hotter than the room, heat flows out. Work is energy transferred when a force acts through a distance, pushing a piston, turning a turbine, or stirring a cup. Heat and work are transfer modes. They aren't properties contained in the system like mass. We often label heat with the letter Q and work with W. Quick examples: put a hot plate under a pot. Heat flows in and raises water temperature. Compress a gas, you do work on it, and its internal energy rises. Both change what's inside the system, but in different ways. Now, the first law. It's a conservation rule. Energy is neither created nor destroyed. For thermodynamic systems, we write it as delta U equals Q plus W. Delta U is the change in internal energy. That's the energy stored inside the system: molecular motion, chemical energy, etc. Q is heat added to the system. W is work done on the system. So if you add 100 joules of heat to a gas and do 20 joules of work on it, the internal energy goes up by 120 joules. In a different case, if the system does work on the surroundings, conventionally W is negative, and delta U can decrease even if heat is added. Practically, this law tells engineers how much useful energy remains after transfers. It's why energy audits add up inputs and outputs. Everything must balance. But conservation alone doesn't tell us direction. That's where the second law enters. The second law introduces direction and limits. One intuitive statement: heat flows spontaneously from hot to cold, not cold to hot, unless we do work. Another formal idea is entropy, a measure of how spread out or disordered energy is. The second law says total entropy tends to increase in natural processes. What does that mean in practice? Imagine a steam engine. You put heat into the engine from hot steam and extract some of that energy as work. But you cannot convert all the heat into work. Some energy must be dumped as waste heat to a colder sink. That's why no heat engine is 100% efficient. Entropy captures that lost ability to do useful work. Refrigerators, for instance, move heat from cold to warm by doing work. They don't violate the second law because you supply energy to make that heat move uphill. In everyday life, this law explains why your coffee cools, why engines run hot, and why order requires constant input of energy. So, why should you care? Thermodynamics underpins everything that uses energy. Power plants, refrigerators, batteries, solar arrays, and even living cells. For example, In a solar PV plus battery system, sunlight delivers energy to panels, panels convert some to electricity, inverters and batteries store and release energy. But each step has losses. The first law helps account for total energy. The second law tells you where the losses limit efficiency. In HVAC, engineers track heat flows and work to size systems and minimize waste. In engines, maximizing work while dumping minimal waste heat is the central challenge. Even at the scale of a phone, battery chemistry obeys these laws. Charge, discharge, heat generation, and degradation are all thermodynamic issues. Learning the rules lets you design better systems or understand why certain perfect devices are impossible. Pop quiz. You add 200 joules of heat to a sealed cylinder. The gas inside does 50 joules of work pushing a piston. According to the first law, what is the change in internal energy delta U? Pause the video if you want a moment. Answer follows. The change in internal energy delta U equals Q plus W, with Q equals plus 200 joules and W equals minus 50 joules if the system does work on the surroundings. Delta U equals 200 minus 50 equals 150 joules. So the system's internal energy increases by 150 joules. Short follow-up. If the surroundings were hotter than the system, heat would flow the other way, and delta U might be negative. These simple calculations are what engineers use every day to balance energy budgets. Recap. Pick a system and surroundings. Energy crosses boundaries as heat, Q, or work, W. The first law conserves energy, delta U equals Q plus W. The second law gives direction and limits via entropy, preventing perfect conversion of heat to work. Together, these principles are the roadmap for all energy technology. If you want, next time we'll dig into engines and refrigerators, or walk through a full solar battery energy audit step by step. If you enjoyed this, download the companion one-page cheat sheet with the main equations and visuals, and subscribe for the next episode. Thanks for watching. Keep asking great questions about energy.